Electric potential, or voltage, due to a uniform electric field. Earlier, the voltage at a point in space due to a charge Q was defined as the potential energy per unit charge in the electric field of Q. So we had K Q over R. This approach to calculate voltage can't be used within the parallel plates because of the great amount of charges present. Voltage will not equal KQ over R in a uniform electric field. Since the electric field is constant between the plates, it is not dependent on the distance between the plates. Hint, any equation with a K in it is not going to be usable in a uniform electric field. For the parallel plate configuration, a simple equation relating voltage and the electric field can be derived by using the relationship of work to potential energy. The potential energy of a system with a conservative field is defined as this. The change in potential energy is going to be equal to the negative work done by that conservative field, in this case, an electric field. Let's start out with what we know. We know potential energy is equal to the negative work done by the field. We know that work is equal to force times displacement. We learned that in AP Physics 1. We also know that the electric force on the charge is QE, the charge times the electric field. So we can replace this F with QE. Now we're going to set potential energy equal to negative QED. Next, let's divide both sides by Q, and we get change in potential energy over Q equals negative ED. We previously learned that change in potential energy is equal to Q times delta V. So we're going to plug this in here. So those Q's cancel, and we get delta V, or the change in voltage, equals negative electric field times distance. The AP Physics 2 equation sheet shows this equation like this. So they've rearranged it to solve for electric field. Electric field equals change in voltage divided by the separation between the plates. In summary, the voltage difference between the two plates, separated by a distance d, or as it's written on the AP2 equation sheet, r, is V equals ED, or on the AP2 equation sheet, they get rid of that negative sign by just putting everything inside absolute value signs. So the electric field between these plates is equal to the difference in voltage divided by the distance between the plates. Since the electric field points in the direction of the force on a hypothetical positive test charge, it must also point from higher to lower electric potential. The negative sign just means that objects in a field feel a force directed from locations with greater potential energy to locations with lower potential energy. And this applies to all forms of potential energy. A more intuitive way to understand the negative sign in the relationship is to consider that just like a mass falls down in a gravitational field from higher gravitational potential energy to lower, a positive charge falls down from a higher electric potential to a lower electric potential. The AP Physics 2 equation sheet has the equation written like this without the negative sign. This equation says that the strength of an electric field between two plates, like this, can be calculated using the voltage difference across a distance. So let's say this has V and this is 0. This will have a delta V equal to that voltage, and the closer these plates are together, the stronger the electric field that will exist between the plates. Let's go over units. The electric field can also be described in terms of volts per meter, in addition to newtons per coulomb, which we've used previously. So you can see here that voltage is in volts, distance is in meters. So volts per meter is another unit you might see for electric field. These units are equivalent. Here's a summary of all of the equations we've learned so far. Now these four can only be used with point charges, and you'll see that we have 1 over 4 pi epsilon naught, which is K, 9 times 10 to the 9th. That is in all four of these equations. So That's your hint. If you see this term in your equation, it can only be used with a point charge. Also remember that electric force and potential energy can only belong to you need two charges in order to have a force or potential energy in a system. Whereas for electric field, that's due to one charge, and voltage is also due to one charge. The other difference is that when you're moving down from force to potential energy, you're going to lose one of these R's, and same over here. If you have electric field, it's over R squared, but voltage is just over R. Here we have two equations that can be used anytime, in any situation. Electric field is always equal to force per charge, and change in potential energy is always equal to the charge times the change in voltage. Here is our uniform electric field equation that shows that the electric field in a parallel plate capacitor is going to be equal to the voltage difference divided by the distance between the plates. Now this equation is handy. It is not on the AP2 equation sheet, but here if you plug V equals ER, or D as it's commonly seen in other textbooks, V equals ER, if you plug that in here, you get a handy version where it's the change in potential energy equals QE times the distance between the plates. Also remember, this equation is not actually on the AP2 equation sheet. So you can derive it using other equations, or you can just remember that it's very similar to force, but you multiply force times distance R, and that will cancel out one of those R's and give you this equation here.